All right, any other homeworks coming in?
Yeah.
Yes, okay.
I forgot to like number them. Can I number
Okay,
them?
yeah, go ahead and number them.
Yeah, I was only getting, I just remember it was only going to be J, and I couldn't use it. Now I'm going fine.
So, a variety of things I'd like to do today. I want to talk about homework questions on the homework that you just turned in. Okay, make sure we're good with that. I want to talk briefly about the next homework, your last homework, which I posted last night or this morning. And then I want to review Lab 6, which was the traffic light you just finished. Then I want to talk a little bit about Lab 7, and then we're going to jump back into working with Verilog for the rest of the class. And this is going to get fairly hairy very quickly, and so it's going to be a bit of an effort probably to stay focused throughout this whole class. But we're going to talk about Lab 7 and the things you need to do to make Lab 7 work, and it's a really complex process to get things working. Once everything is working perfectly, it's really, really easy to use Verilog and the tools and all this kind of stuff, but getting there takes a fair amount of work. So we'll go through that, thanks, very carefully. All right, so let's start with homework 6, which you just finished, which was actually homework 5. So questions about this? Yeah?
Sometimes it wasn't clear if we should include Z in output into our equations or
so like which questions do you remember?
I don't really know, but I noticed that, but I feel like for the most part, like it was kind of.
Yeah, how do you define Z?
Yeah.
So for example, a 2-bit binary down counter should be outputting a 2-bit number, right, that counts down. So you're going to have 2 outputs, right? Z1, Z0, or whatever you want to call them. Z is usually used for outputs, but it doesn't have to be. So a counter, the output is, the count value. So a binary counter that counts from 2 to 7. So there you're going to need 3 bits for your output because you need to represent the numbers 2, 3, 4, 5, 6, 7. Right? 7 takes 3 bits. Question 3, you're told one output Z, so that's straightforward. Question 4, design a finite state machine according to the following rising edge. So it looks like, yeah, well, this one's a good one to ask for clarification on. But if you asked me for clarification, I would tell you that I believe Y1, Y2 are the state number. Let's see, Y1, Y2, if they're both 1, you're in B. A 1, 0 looks like you're in C. Is this consistent? Yes. And a 0, 1, 0, 0 looks like A, and 0, 1 is illegal. So I believe that the setup here is that Y1 and Y2 are just the flip-flop outputs, right? The values of the 2 flip-flops, which you're using to encode the state A, B, or C. And then RCO is the only output that's generated by your circuit. But if you build it with 3 outputs, Y1, Y2, and RCO, that's fine, but Y1, Y2 are just going to end up coming from the flip-flop outputs. And then 5U, so there's an output specified here, which is Z, so that's just your 1 or your 0, which tells you if you're sad or not. And then 6, I believe I said just do a circuit state diagram, and you can just go into a state when you want to unlock. I mean, technically you could have an output that says is the system unlocked or not, but it's going to be 0 unless you're in this magic final state after you hit star 2, 3, 6. So I don't mind if you don't have an output specified there. And then 7 was gray code counter, so 3 bits, so 3 outputs. So you usually can't go wrong with putting in outputs if you're not sure, but definitely always ask, especially if you're doing it on a test or something, and I can clarify. we talked about gray code counting, right? Like why this sequence is interesting. So what do you notice as you go from one sequence to another? Is this a separate question? Or?
That's a question.
Okay, hold on then. So you notice anything in particular when you go from one number to the next, other than they're out of order?
It only changes one bit.
It only changes one bit at a time, right? That's what a gray code counter does. And that's useful because we might be using those bits to represent a state. And so let's say we have a system where we say this is state A, B, C, D. And suppose our system normally goes from A to B to C and back to A. And your input is your temperature control. So let's say this is a nuclear plant controller, right? And your input is the overheat detector, right? So if your input's 0, everything's running normally, and you move from state A to state B to state C and back to the beginning, and that's just what this thing does. But if your input is ever a 1, it takes you to state D, which is like the national emergency state, which says the reactor is overheating, and so it calls the governor automatically and everybody evacuates, and this kind of stuff, right? So normally it just goes A to B to C. So if you use flip-flops like this to number your states, right, you go from A, which is a 0, 0, to B, well, this bit changes to a 1, so now you're in state B. As you go to state C, what's going to happen? Well, this bit's going to change to a 0, this is going to change to a 1. What happens if that second bit changes to a 1 first, before that first bit changes to a 0? For a really brief instant, your system hardware says, oh, we're in state D, and it makes the robocall to the governor, and now you've got a really bad situation, right? It's a glitch. In moving from this state to this one, we inadvertently, temporarily go through state D. Okay, we could eliminate that possibility oh, I'm lying to you. Well, work with me anyway. It doesn't work, I set it up badly. But the idea is with a gray code, right, when you go from one state to the next, you only have one bit changing at a time. So it doesn't matter how quickly this state changes from a 0 to a 1, this output, you're either going to be in state 0, 1, or whatever that next state is, and I would number these A, B, C. But my analogy doesn't work because going from C to an A, you've got another potential glitch. But assuming that you're using the full gray code sequence, so if I had 4 states here, right, when you go from one to the next, to the next, to the next, and back to the first, you can't have a glitch, right, because only one bit changes. So it eliminates a potential race condition that can give you an illegal value. All right, so questions on any of these? I don't know which one I'm going to grade, but I'll probably look at a few of them. All right, so how did Lab 6 come out? It was a lot of work.
Good payoff.
You got it going? Cool. And we got the traffic light test bed working, by the way, Vlad.
Oh, we did?
It does work, yeah.
Okay.
Two of your red lights were inverted, right? But one of them wasn't. One of them was actually connected to ground.
Okay.
I don't know why one of them was done differently, but so I rewired the test bed for that one. But it works other than the one yellow.
Okay.
So that's still hooked up in there. You had a question?
It was about the homework.
Yeah, yeah.
When you're solving for Z, it says that, and I know like pretty much every circuit in the homework has to have output. I was not able to figure out Z because it depended on the homework asking. So, but my question is, how do you define Z if they don't specify the output?
If they don't specify an output, then you don't have an output, right? And it doesn't have to be Z. Z is just the variable, but I think you're asking how do you specify the output if it doesn't tell you what the output is?
Yeah, some questions are like by common sense you know that there is an output.
Yeah.
There's another one that it's just questionable.
Yeah, yeah.
What the output should be.
So if you're not sure, just ask. Would be the easiest thing. And the more that you ask and you see examples where you do have an output or you don't have an output, the more you'll figure out what that process is. Like the counter questions don't explicitly say generate a 3-bit output, right? But a counter, by definition, is a circuit that you put in a clock, and every time the clock ticks, the output increments, right? That's just an experience thing. So if you're not sure, just go ahead and ask. And on the homework, if you're moving from state to state correctly and you're not explicitly generating outputs, that's not a big deal for me. So the trickiest part is coming up with the machinery for the flip-flops and how to update the state of the system. And the output's usually just another piece of random logic based on state variables or inputs. So it's just a combinational thing. So one comment on drawing circuit diagrams. So I noticed this in some of the schematics from Lab 5 and from Lab 6. Suppose you are building your traffic light circuit, right? You know that if you have an AND gate, you draw a picture of the AND gate with the regular AND gate symbol, right? You label the pin numbers and you put a package designation, like U1 for example, and up here in your component ID block, you say U1 is a 74LS08, and you've got VCC on 14, ground and 7, and whatever your no connections are, right? So you can do the same thing for all of your chips basically. In particular, if you have a flip-flop, let's say you've got that octal flip-flop set up, right? Go ahead and draw something that says like D flip-flop, and have a D input, and have a clock, and have a Q output. And I don't know what the pin numbers are, so this is fictitious, but maybe the clock on this chip is pin 1, and the D input was 3, and the Q output was 2, and I would designate this U2, and U2 would be a 74. I don't know what it was. I don't think it was a 368, but whatever that 8.
The other thing is 374.
374? Yeah, it was close. Thanks. And I think VCC was 20 and ground was 10, and so on, right? But this is more useful than, say, drawing, you know, a picture of a chip and just connecting to these things, because yeah, that's useful for wiring it, but to look at the diagram and know what your circuit does, this is more meaningful than a rectangle labeled 7408, right? This is an AND gate, this is recognizable. This is a way we can draw a D flip-flop, right?
Is there a shortcut for 555?
So for 555s, it's a little weird, right? Because, yeah, so not really. So for 555s, you just kind of draw the 555. Same with the 7-segment decoder, right? You can draw the picture of the chip, but label your inputs, you know, A, B, C, D, and your outputs A, B, C, D, E, F, G, or whatever they are. And there's a LT bar, right, which gets connected to ground, and it's not a precise science, but this is more meaningful than just a rectangle with pin numbers, right? Even though that's all you need to actually build it. If you know from looking up here, this is a 74LS47, and you look up that, it's like, oh yeah, 7-segment decoder. Okay, so you know those are the 4-bit values, and these are the segment outputs. So just labeling your blocks in a way that matches the specification makes it a little more usable to someone who's looking at the circuit. And it's another one of these sort of like, takes practice to find like the right level of detail. But flip-flop pictures are very standard, right? Logic gates are very standard. But we're done with circuit diagrams. So. All right, so lab 6, yeah, lots of work. Have we talked about how to debug circuits? I've been working with people in lab when they have a circuit that doesn't work, but I haven't worked with most of you. So I'm just going to draw a fictitious circuit. I don't know. I'm making this up. Don't try this at home. Alright, so a sloppily drawn, but functionally correct wiring diagram for your circuit. And you're supposed to flip the switches and the red light should come on, or you flip them some other way. The green light should come on and some other way they should both go off or something, right? And you build your circuit and you test the switches and none of the LEDs are lighting, right? And you're not sure what the problem is. So you let's call this A and B, and you've got a truth table, and let's say if A is 1 and B is 1, then red should be 1, and I don't know what green should be. But here's a combination. If I have both of these open, the red light should be on. Okay, and you open up these switches and the red light is off. Okay, so how do you figure out what's going on? So grab a multimeter, okay, get some alligator clips, take the ground probe, the black one, connect that to ground somewhere on your circuit board. And then take the other probe, connect that to an alligator clip, connect it to a wire. Okay, so the first thing you do, take that wire, that's your probe, you can put that anywhere in your circuit board and read the voltage, right? Put your multimeter on voltage, flip down the stand so it's just standing up so you can look at the display easily, and put it right here on pin 6 of U2. Okay, so you might want to make a little sketch. You did this in your lab report, this was good. Make a little sketch of where your chips are. Right, here's U1, U2, U3, and here's red and green, and here's A and B, or whatever, right? So you look at your circuit diagram, okay, pin 6 of U2, I believe, should be outputting a 1. So that's that middle chip, go to pin 6 of that, 1, 2, 3, 4, 5, 6, put your wire in there, read the voltage. If you're reading 5 volts, then you've got the correct output here. And the fact that the LED is off means one of a few things is going on. The LED is bad, the LED is backwards, or this side of the LED is not connected to ground. Right, so you take the LED, double check the polarity, right? If the polarity looks right, stick another LED in there. If it's still not on, check your resistor. Is it actually a 1K or is it a 10K? Because a 10K looks a lot like a 1K. Right? Check the other end, is it really connected to ground? Maybe it's in a ground bus, but that bus isn't grounded, right? But as soon as you measure the voltage here and you see a logic 1, 5 volts, you don't have to worry about any of this. You know your problem is somewhere right here. But if you measure right here and you've got a 0, right, something's wrong over here. Okay, well, I believe that this would be a 1 because I thought that, let's say, this input 4 was going to be a 1. So take a voltage reading right here. If that's a logic 1 and this is an OR gate and the output is 0, there's a problem right here. So what's the problem? Well, maybe it's not an OR gate. Maybe the OR gate is broken. Maybe the OR gate's not powered correctly. That's kind of it. So look at where power and ground are, take voltage readings there, should see 0 volts, 5 volts. Read the number on the top, make sure it says 74 LS, whatever an OR gate is. And if all of that looks correct, try a different OR gate. And you pop this one out and you say, oh, pin 7 is broken, right? So it wasn't getting power, so you put another OR gate in. But if this is a 0 and I believed it should be a 1, that's a problem, right? So where does this come from? It comes from pin 3 on U1. Okay, U1's up here, 1, 2, 3, count down to pin 3, take a voltage reading right there. If I've got 5 volts there and I had 0 volts here, there's a problem with that wire. But basically you're tracing the problem back through your signal from the output that you know is wrong until you find the problem. But you can't do this unless you got your wiring diagram, right? This is why Izad and I are always telling people you got to do the wiring diagram first. Because if you have this, this is how you can start here, work your way back. And eventually you're going to find something where, you know, this is outputting a 1, this is outputting a 0. Okay, there's my problem. I connected this to pin 3 on the wrong chip. All right. And it's very methodical to find a problem with a circuit at that point. Other than the fact that you've got 100 wires you have to work through. So when I was growing up, if you bought a TV set or a radio or anything else, if you took off the back chassis, there was always a schematic diagram inside. And it was so that if your TV or radio stopped working, you could do the same thing. You could get out your multimeter, or maybe your oscilloscope, and you could start tracing through and figure out where the problem is. They don't do that anymore, right? And most of the stuff is in a single computer chip, and so you always see this thing that says no user serviceable parts inside, right? Which I think the lawyers make them put on so that you don't shock yourself when you take the cover off. But this used to be sort of standard in any piece of electronics, so that you could actually go inside and troubleshoot. And so you can do that on your circuits as well. So if I didn't get a chance to work with you in this course for that, if you have me for 270, definitely catch me and we can go through that. All right, so lab 7. So this is different from the lab 7 that was up there before yesterday. So I've posted a new version of this. Actually, a version that Izad put together from my old version. So lab 7, yeah, and it's not VHDL, it's Verilog, but that's okay. That is not lab 7. This is lab 7, all right. So lab 7, we're going to play with Verilog. And as I said, this is not something you have to do in the collaboratorium. There's no circuit building involved here. So no protoboards and no test equipment, things like that. It's all software. And we'll run through some of this software in a little bit, and I'll show you some of the things you can do with this. But let me give you a bit of a disclaimer / warning up front. So we talked the other day, right, how chip design is like really expensive business, right? Millions of dollars to make one version, one copy of your chip, right? A lot of money in this industry. And so historically, the software that's used to do circuit design, to do testing of circuits that you designed and so on, historically really, really expensive, right? Hundreds of thousands of dollars to get a copy of this software, because that's where people were making their money, right? And these programmable devices, these physical chips that you can load ones and zeros into and turn them into some other piece of circuitry, that's big business. So primarily a company called Xilinx and a company called Altera. Altera got bought by Intel last year. They're the two big players in it. Okay, Xilinx and Altera. Probably Xilinx is number one. And they make a lot of money selling these devices. Years back, they discovered that the real source of the money was the software that people use for these devices, because the chips are inexpensive to make. You just keep turning the crank and more chips pop out, right? But they make their money off of the software. And people can write their own software, right? We're programmers, so we can write code that does what these expensive tools do, except the way that you program these chips is a secret. And they guard the secret very closely. So the actual ones and zeros you feed into this chip to turn it into an AND gate or a multiplexer or a traffic light controller, that's proprietary information to the chip manufacturer. It used to be open. In the early days, they had a line of chips that this was totally public knowledge. And the community went crazy. They started making all kinds of tools to program these chips. And I think Xilinx saw like future profits dwindling before their eyes, right? So, so they've clamped down the configuration information, and it's closely guarded secret, and it's extremely hard to reverse engineer. A few people have done it. So you're kind of at the mercy of the software tool chain that a manufacturer gives you. If you want to use a Xilinx chip, you got to get the tools from Xilinx. If you want to use an Altera chip, you get the tools from Altera. This is all preamble to the observation that when you have closed source software, the quality can get really poor, and there's nothing stopping that from happening. Right? If the only company that makes software for programming Xilinx devices is Xilinx, it can be terrible software, it can be fantastic software, it doesn't matter, everybody's going to use it. So that's a bit of a preamble to a warning, which is this software is not the most pleasant software in the world to use. Okay? It's fairly painful. It's got some bugs. It's a huge suite of tools, right? So it's not surprising that it has bugs, but when there's a bug, it's up to the developers at Xilinx to fix the bug. And if it's not affecting their sales, what's their motivation to fix it? I don't know. So I want you to be prepared as you're working with this stuff to have a bit of a different experience from, say, using Microsoft Word, right? Or whatever your favorite pieces of software are, where there's large competitive forces to make sure the quality is as good as possible. So that's the first thing. Yeah?
That's kind of a sub-tangent. If you were to reverse engineer it and then post that good code online, would that be illegal?
I suspect so. I suspect to actually do anything with their chips, you're somewhere signing an end-user license agreement, which says no reverse engineering. It would certainly make them very unhappy. And yeah, I won't pontificate on that further. But I was in a community that was benefiting greatly from the open source aspect of their earlier chips, and that community kind of crashed when things got closed.
Did you provide a free download link for the software?
Yes, so there is a version of their software which is free to use for non-commercial purposes. And if you go to this, and I can't click on this from my PDF, but you can copy and paste it, it will take you to another document which has a link for downloading. Okay, so that's a free download. You have to get a license. The license is free, but you gotta give them your name and email address, and they'll confirm your email address, and then you use the license when you install the software. Okay, so we had the software installed on the machines in the collaboratorium last spring. For some reason, they don't seem to be there right now. So I'm going to double check this afternoon and see if they're on any of the machines. If not, you have two options. Well, you have a few options. Your best option is to install the software on your own machine. Okay, if you're running Windows, that's very straightforward. If you're running Linux, I can help you with it because that's what I've got. If you're on an Apple, you can try it, but I don't know if they support
Just get an app on this.
Apple or not. What?
You can just get an app on this if you have.
Yeah. But if you don't install on your own machine, right, you should be able to install this on the Collaboratorium machines. And it takes maybe 5 minutes to download and install, maybe 7 or 8 minutes. So it's not something you can do if you just got 10 minutes, right? But if you're going to sit down for an afternoon and work on this stuff, you can download it and install it on those machines. That's what I'm going to try to do after class and confirm that it'll work. Your third option, Izod has copies of what you would download on flash drives, and you can install from that if the download link has moved or something. And that's the version that we know used to run on the PCs in the Collaboratorium. And you can use those to put it on the Collaboratorium machines or your own machine. It's a lab, so you're working in groups, right? So if at least one person in your group has a PC that you can install this on, you're good to go. So for what we're going to do, the software seems to work really well. But it's not unheard of to try to use Verilog to build a large circuit, and you hit the go button and it runs for 72 hours and it's just churning away on it, and you come back in the morning of the third day and there's a message saying, you know, unknown error, please try again. Right? It happens. It's a phenomenally complex thing, right, what's going on inside these tools. So it's almost impossible to imagine that it's not going to have bugs and glitches. But for what we're doing, it should work well. Okay, so let me start with a lab. Right, so this is Lab 7. This is the one that's posted under Lab 7. And I put a link in there to 2 documents. One is an introduction to Verilog. Okay, so this thing, which we started working through on Tuesday. And the other thing is, the second link after that is this introduction to Verilog using Xilinx ISE Webpack. That's the software we're using. Okay, and that's what this link would take you to. So you can copy and paste that to get to this document, or you can just grab it straight from Canvas. So let me see what I want to say about this. So if you're going to install it on your machine, download, just follow the steps and try not to deviate from the steps unless it's forcing you to, because I went through this and I found the things that would make it work, and there may be other things that make it work, but there may be other things that just send you down a long and lonely path. So after you install it, you need to get the free license, and it usually pops up something which says, you know, would you like to configure your license? And you say yes. So connect now, put in a valid email address so it can send you a confirmation. Follow that, and when you're done, you end up with a file called xilinx.lic. And that you can stick on a flash drive, so that the next time that you install the software, you can just take that license file and point to it. And there's some things if it's not working, and these fix some of the problems. Alright, so I'm going to go through some of this live and show you what kinds of things the software does, but this is a step-by-step to load in a sample design in Verilog and simulate it. And the end result of this is a set of timing diagrams. So all of that above there was the process of writing a Verilog file to implement an AND gate and then simulate it. So this gate has 2 inputs, A and B, and an output out. And so the simulation started off with A being high and then dropped it to a low. And then B started off low, went high for a bit, and dropped low. And you can see the output. If A is 1 and B is 0, the output's low. when both A and B are 1, the output is high, and when A is low and B is high, the output's low, and when they're both low, the output's low. And so that's your verification that you've successfully designed an AND gate, right? And we've put all the possible combinations of A and B into it, and the output is 1 exactly when both inputs are 1. And the Verilog for this is, it's hard to see this one line, assign out equals A ampersand B, which we started to look at last class. So you're writing like, 3 lines of Verilog, and then you're doing like a million things to compile it and simulate it. All right, and you should go through the first 2 sections of this, okay? Don't worry about section 3 yet. So this is going to be the optional lab that you can work on if you like, where you actually take a piece of hardware and you program it to be whatever circuit you're designing. Okay, and that's what sections 3 through the end of this document talk about. But we're not going to worry about that for now. So let me go through the lab, and then we'll take a quick break, and then we'll come back and we'll talk some more Verilog, and we'll go through some of the steps on the actual software. So lab 7, experiment 1 is simply getting the software running, right, and going through the first 2 sections of that document we were just looking at. And your write-up for here is, for this experiment, we downloaded the software and went through the first 2 sections of this document, and tell me what happened, okay, observations. Now you don't have to repeat verbatim everything that's in that document because you can put a link to that document, right? But we ran the software and the machine crashed. Put that in your report, right? We tried it again and the machine didn't crash, but the software hung up. So then we tried doing this thing and we ran it and it made it further, but we got syntax errors in our Verilog, right? And eventually we figured out we had a missing semicolon, and we ran the experiment on the AND gate, and it looked like it worked like an AND gate. Here's the waveforms that it generated, and put a picture of your waveform, right? Something to tell the reader what you did, what you observed in experiment 1, and hopefully the punchline is that you went through sections 1 and 2 and everything worked fine in the end. Okay, and then the last 4 experiments are actually designing circuits using Verilog. So experiment 2, you're going to create an 8-bit even parity generator. Have we talked about parity? So parity is just a fancy way of saying count up how many ones you have in something. So even parity, we want the number of ones should be even. So parity is a way to do error checking. So you're sending information across a computer. We know about Ascii codes, right? It's an 8-bit code for storing letters as a bunch of 1s and 0s. So this is the Ascii code for the letter A. This is the Ascii code for the letter C. So imagine that I'm entering grades and you've got an A in the course, and I type in an A and it gets sent as this string of 1s and 0s, but at this moment there's a solar flare that hits the earth and that 0 turns into a 1. And the computer receives this number for your grade entry, and now it records a C. Right? So is that a concern? Okay. So how do we deal with that? We put parity on this. So we add a 9th bit, which we call the parity bit. And we set it to either a 0 or a 1 such that the total number of 1s, including the parity bit, is even. Okay, you can do odd parity too, but if you're doing even parity, we want the total number of 1s to be even. Well, right now my number has 6 zeros and 2 1s. 2 1s, that's an even number. So I'm going to set my parity bit to a 0. Now, 9 bits, total number of 1s is even. Okay, well, if I send this 9-bit number and the solar flare toggles this bit from a 0 to a 1, the computer gets this number. What does it do? It adds up the number of 1s. 1, 2, 3. Hey, there's an odd number of 1s. Something is wrong. Okay, so it's going to say, hey, got a parity error, go ahead and resend that last character. And you'll send it again, and hopefully it'll come across like this. Yeah.
What if we change 2 of the 0 bits to 1?
Then you got to see. Right, so if 2 bits change or 4 bits change, right, this does not detect it. If the parity bit gets flipped, you'll still detect that. Okay, but if 2 bits change, you won't notice it. The other thing is, if your whole transmission line goes dead and everything you send comes across as just a bunch of zeros, that's going to look perfectly valid. Because bunch of zeros, number of ones is 0, that's an even number. So sometimes you use odd parity, which basically says you need an odd number of ones. And now if you just sent all zeros, like your line got grounded or something, you'd notice there was a problem. So there's better forms of error correction and checking. There's ECC, which uses 3 bits and can detect errors and also correct some of them, and so on. And we talk more about these in things like CSE 215. So experiment 2, you're making an 8-bit even parity checker. So what does that mean? It means you want to know how many ones you have. Is it an even number or an odd number? So the system will accept an 8-bit data and output a 1 if there's an even number of ones. Otherwise, outputs a 0. So 8 inputs, and you get 1 output, which is either a 1 or a 0. Experiment 3, you're making an 8-bit up-down binary counter. So a counter that has an input that can say go up or go down. And each time the clock ticks, it counts up or it counts down. Experiment 4 is a shift register, so it's like your delay circuit from lab 6, but instead of having 1 clock tick delay, it's got 8. You put in a value, and 8 ticks later, it pops up on the other side. And that's just what we call a bucket brigade formation. So all of these get clocked together. And whatever bit you put here, after 1 clock tick, it shifts into the second stage. 2 clock ticks, it goes here. 3, 4, 5, 6, 7. Put 1 more on there. And after the 8th clock tick, it comes into this last stage. So it's a shift register. This is really great if you like playing music. You can make a nice delay system with this. Digitize your music, feed it in through a delay like this, and depending on how many clock ticks it takes to come out the other side, you get a version of your music delayed in time. You can mix that with your original and you got a nice echo effect. You can also take that and feed it back in, you can get a reverb. Okay, and experiment 5 is what we call a 5 out of 6 16 event detector. So this should always remember the last 16 inputs. Okay, so it samples input on the rising edge of a clock, and it remembers the last 16 numbers that it sampled. And any time that 5 of those last 16 values are equal to 1, your circuit should output a 1. In any other case, it should output a 0. That's going to have 1 input, 1 output. But it remembers the last 16 values that were input, and if exactly 5 of them were 1, it outputs a 1. And so there's a picture of, there's your clock that's always running. Here's your input, your output is 0 through all of this. Until over here at this clock edge, now the last 16 samples included 1, 2, 3, 4, 5 ones. So now the output goes high. On the next clock tick, now the last 16 samples include 6 ones, so the output goes low. And at some point in time, this first input will fall outside the window of 16, and you'll be back to having 5 of your last 16 be high, your output will go high again. All right, so a variety of experiments, some combinational, some sequential. And we're going to talk about sequential circuits in Verilog after break, and then I'll show you some show and tell with the software. All right, so let's take a 5-minute break. Let's come back at 5 till, and we'll do some more Verilog.